We're going to be finding the volume found when you take the region defined by y equals x squared and y equals 4x minus x squared, and then rotating that region about the x-axis. As is always the case when you have a volume of rotation like this, you want to find the x-intercept so that you can draw an accurate graph for what's coming. So I'm going to set my two equations equal to each other to find out where they intersect. This becomes 2x squared minus 4x equals 0, which I can factor and get two intercepts at x equals 0 and positive 2. Okay. Now I go to a graph. Okay. Both of these are quadratics. This is a quadratic with vertex at the origin and opening up. This is a quadratic that has x-intercepts at both 0 and 4, and it opens down. So it's going to look something like this. Okay. So here is my original region. Okay. Now I'm going to take this and rotate it about the x-axis. So it's going to look like another copy popped up here, and then it's going to look like a bowl-like shape. Okay. All right, now there's multiple ways to solve this. The one we're going to look at is the easiest method of slicing, or at least the easiest to visualize, which is that if this is my axis of rotation, I'm going to slice perpendicular to that and take a really thin slice that way. Now, if you think about that, this is a bowl. It has a giant hole in the middle. So this shape is what we call a washer. Okay. Now, the volume of a slice is going to be approximately the volume of that washer, which we find by taking the volume of the outside cylinder and subtracting the volume of the cylinder that's the hole in the middle. So that's pi r squared minus r squared h, where I use capital R for the biggest radius and little r for the small radius. Okay, so now I need to plug things in here. As I just mentioned, capital R is the big radius. That is, starting from the center of my washer and going towards the outside. And once again, I chose to go up because I want to go through the original region. Now, if you look at that, that looks like a y-coordinate of this curve. Okay, so the y-coordinate of that curve is 4x minus x squared. Now for my second radius, I'm going to start at the center and this time only go up to the top of the hole. That also looks like a y-coordinate, but this time of my other parabola, which is y equals x squared. Once again, I was slicing in this manner, so my h is a little delta x. All right, now I'm going to add these up and stick a limit in front of them, which has the effect of turning it into an integral in front of here. However, it is always within my best interest to clean this up a little bit before I actually try to integrate it. It also saves me from having to do some u substitution. So, first I'm going to multiply this all out. I get 16x squared minus 8x cubed plus x to the fourth minus x squared. And then combining like terms here. Okay, oh, excuse me, this is an x to the fourth. I get 16x squared minus 8x cubed times pi and delta x. Okay, now when I take the integral to find the full volume, it's pi times 16x squared minus 8x cubed dx. And the limits of integration are as far as I go for my full volume. Since I'm doing x, I look at the leftmost x-coordinate and the rightmost x-coordinate, which would be the 0 and 2 that I found earlier. Okay. Now I'm going to take an antiderivative. I get 16 thirds x cubed minus 2x to the fourth, evaluated from 0 to 2, and of course with a pi still in front. 16 thirds times 8 minus 2 times 16. And of course the last term is just a giant pi times 0 because I'm plugging 0 into everything. Okay. When I add these all up, I get 32 pi over 3 for the volume of my solid of revolution.